A plus B equals 14. B plus C equals 18. A plus C equals 16. For most students, seeing a stack of equations like this triggers an immediate sense of friction. The difficulty here is purely cognitive. Your brain is attempting to juggle three invisible relationships at once with no physical map to help. Formal algebra is a precision tool, but it operates like a strict language. If you don't already speak it fluently, the symbols offer no clues on where to start or how the numbers actually connect. But what if we stop treating this as a calculation problem and start treating it as a spatial one? We can take the exact same data and redraw it into a puzzle our eyes can solve. Most people who feel they are bad at math are actually just running into a failure of translation. This is an arithmogon. It organizes data from separate equations into a connected map. The rules are simple. The corner circles represent our unknown base numbers. The edge boxes show the sum of the two circles they connect. Geographic organization lowers the mental energy required to solve the problem. Instead of holding equations in your working memory, you can simply follow the lines of the triangle. Here is our initial problem again. We have three totals on the edges, 14, 16, and 18, but we don't know the values in the corners. Rather than looking for a single variable, we look at the whole system. If we add up all the edge totals, 14, 16, and 18, we get 48. Look at the connections. Because each edge box touches two circles, adding all the edges together means we've just counted every corner value twice. If 48 represents 2 of every circle, then a single set of all 3 circles must be exactly half, 24. Now we just subtract what we know from that total. If we take the bottom edge, which we know equals 18, and remove it from our total of 24, we're left with the top corner. A must be 6. Once one corner is solved, the others fall into place. If A is 6 and it adds to B to make 14, B is 8. If B is 8 and it adds to C to make 18, C is 10. By prioritizing spatial logic over memorized formulas, we've turned a source of frustration into a simple exercise in deduction. This framework isn't limited to addition. Once you understand the geographic relationship, the logic scales to other operations. This version works for multiplication. The edges now represent the product of the two corners, like A times B. Visual models build an intuition for how variables interact, turning abstract mechanics into something observable. When we compare the spatial solution with the formal algebraic proof, the overlap is perfect. The visual shortcut of adding the edges and dividing by 2 is the exact same logic as combining equations and factoring out a coefficient. Arithmogons ground these abstract rules in a physical layout, making the logic of the symbols visible before you ever have to write them down. Proficiency in math has less to do with calculating numbers and everything to do with organizing information efficiently. This applies whenever a problem feels intractable. If the current view provides no path forward, the first step is to seek a representation that reveals the hidden connections. When the symbols stop making sense, don't just stare at the page. Change the translation and draw a better picture.